Hello guys, welcome to my channel. I will propose some short problems in classical mechanics. This bunch of problems that I will be posting are meant for undergraduate students taking a bachelor in physics or engineering or maths. So let's get started. I will start reviewing some fundamental concepts like velocity, acceleration, etc. And the first exercise I bring you today is about ballistic trajectories and precisely about Tartaglia, which was an Italian mathematician and engineering. And the problem goes like this. In 1537, Tartaglia published his Nova Scintia, where ballistical trajectory problems are described. In it, he proposes a three-part scheme to describe the trajectory of projectiles. The trajectory consists in two straight lines smoothly connected by a circular arc of radius r, capital R. Let's assume that the speed of the projectile is given by v equal kt, where t is time and k is a positive constant, and t is the last time from the beginning of the motion. If pi over 3 is the angle between the normal of both straight lines, and assuming the particle entered the circular path at t equal t0, find the projectile maximum acceleration. And we are given a solution, this formula here, where we have to arrive. Okay, so let's get started. Here is my proposed three-part scheme. Here is the first part. This is a straight line. Okay, second part here, second straight line. And we are said that the normal of both lines form pi over 3. This means normal here to the second, normal here of the first, and this angle is pi over 3. Is pi over 3. So the acceleration has two components. We are asked for the maximum acceleration. The acceleration has two components, tangent and normal. And the formula is this one. The tangent component of the acceleration of a particle traveling along a curve is the derivative of the speed with time, and the normal is given by the square of the speed divided by the radius of curvature. We are told that the speed varies like k proportionally with time, k constant t time. So on the first part, the straight line, the radius of curvature is infinite because it's a straight line. So this part here, the normal component is 0. The same happens for the third part, this straight line here. Radius of curvature is infinite, so no normal component. The situation changes here, of course, along the circular path where the radius of curvature is simply r. So we get that the acceleration is k tangent plus the square of the speed divided by the radius of curvature normal. And we just substitute the speed here, which is k squared t squared divided by r, normal component and tangent component. So the acceleration will be maximum, of course, along the circular component because we also have a normal component here. In the magnitude of the acceleration, since both tangent and normal vectors are perpendicular, is the square of the component square. Is the square root, sorry, about component square. So we have a is the square root of k squared plus this thing here square, k4 t4 t power 4 divided by r squared. So the acceleration will be maximum when this t here, t is maximum. And when will this t here be maximum? Well, if it enters the curve and the speed varies linearly with time, then here the speed will be maximum. The normal component will be maximum here when it exits the circumference. Okay. And to compute this maximum time, we simply remember, we take into account that the speed is the variation of the length of the curve, of an infinitesimal length curve with time, and along a circumference, this is just the radius multiplied by a certain angle. We first set an arbitrary angle here along the curve to perform the variation. Okay. Since the radius is constant, it jumps the derivative and we just get radius multiplied by the derivative of the angle with time. And this must be, of course, equal to kt, since we were told from the beginning. And this is just a simple differential equation, first order ordinary differential equation, and it is separable. So we just separate here in angle and time and integrate between 0 and p over 3, which we are told since the beginning, and t0 when it enters the curve, and t final, t that we call t maximum, when it exceeds the circumference. We perform this simple integral, and then we arrive to an expression like this. So all we have to do now is just solve for t maximum square, just by solving this here, leaving it alone, and we get this expression here. Okay, of course, depending on the radius of curvature, the constant, and the initial instant when it enters the curve. And all we have to do finally is to get the maximum acceleration is carry this here, t maximum square, to this formula before that we got before for the magnitude of the acceleration. So we just substitute here the maximum 4, and we finally arrive to something like this. We carefully substitute and we will arrive to something like this, which is coincides with what we were told at the beginning to arrive to. Okay, for those of you that say, okay, and how do you know that the acceleration is separated and in tangent and normal components? Well, suppose here, let's assume this is a curve, okay, a curve, and here is an infinitesimal path of the curve. Here is the projectile traveling with velocity v, and at a certain point we have a tangent to the curve and an normal to the curve. So the velocity, of course, is tangent to the curve, which tangent vector I will call tau, unitary tau. Okay, if we want to compute the acceleration, we have to go for the derivative of the velocity with time. And the velocity is v tau. And if we apply the chain rule here, we have, of course, the derivative of the velocity of the speed with time, tangent plus the speed, and the derivative of the tangent vector with time. And the tangent vector varies, of course, we see here, it varies along the curve. This vector is not the same as this, and this. It of course, varies with time, but it varies with the infinitesimal arc of the curve, infinitesimal length of arc of the curve. So this derivative here, applying the chain rule, is derivative of tau with time is derivative of time, tau, sorry, the unitary vector with s, multiplied the derivative of s with time. But this is simply the speed. So it jumps here, and we get that the acceleration is the derivative of the speed with time, tangent plus a square of velocity, a square of speed, derivative of the tangent vector with respect to the infinitesimal length of arc, length of the curve. To compute this derivative here, we come here to the left, and we know that the tangent vector is unitary. If we derivate this with the length of the curve, we get that the derivative of tau with s multiplied by tau plus tau derivative of tau with respect to s must be the derivative of 1 with respect to s, that is 0. Just simply applying Leibniz chain rule for derivatives. Okay, so this is simply 2 tau multiplied by the derivative of tau with respect to s. This is equal to 0. So this means that tau must be perpendicular to the derivative of tau with s. Or in other words, that the derivative of tau with s must be parallel to the normal vector at that given point. And we can call that the derivative of time, we can define derivative of time with respect to s is a constant k, a certain constant k, multiplied by the normal vector. And we carry this here, and finally we arrive that the acceleration is the derivative of the speed with time, tangent, plus the square of the speed multiplied by a constant and the normal vector. By definition, this constant is the inverse of the radius of curvature of the path at that certain point. So finally, we get that the acceleration is the derivative of the speed with time, tangent, plus the square of the speed divided by the radius of curvature, normal component. So Tartaglia was an Italian mathematician and engineering, and in 1537 he described this. He performed several studies for ballistical trajectories and the cannonballs, and he was then superseded by Galileo, another um, celebrity in physics and science. Okay, for suggested reading, I propose this. There are several very good books in mechanics. Here, the very good books and quite well known are Goldstein, of course. He describes in an introductory chapter fundamental concepts like velocity, acceleration. Kibel as well, classical mechanics, very good book from Imperial College. Landau Lipschitz, this was from the Russian Academy of Science. And I really like this book because he condenses a lot of information in very few pages. Another very good book, Marion, Classical Mechanics, Classical Dynamics of Particles and Systems. Quite dense, similar to Goldstein, different styles, but very good as well. So any of those are very good and suitable for an undergraduate course in classical mechanics. Okay, guys, thanks for watching. Hope you enjoyed it, you liked it, and practice math and stay curious. Bye bye.